Well, I'm okay to start. I can use those extra minutes. So thanks a lot for inviting me to give this very first talk. So I'm very happy to have the first talk. As I said, right, I mean, with 21 centimeter cosmology, you can either be the first talk or the last talk at many conferences. I'm always happy to be the first one. So thanks for that as well for the organizers. So I will talk about advances in detecting the 21 centimeter signal of the epoch of reionization with low FAR, but I will also add nano FAR to it because we're making quite significant results, progress on our observations with nano FAR, which I will introduce during this presentation. And in the next talk, you'll hear a little bit more about this as well from Flora Mertens. Now, of course, right, this is the 21 centimeter cosmology, but I think I should at least show a few slides on the enormous progress that's currently being made with JWST at very high redshift, right? We're really witnessing a change in our understanding of the infant universe, so the first billion years in terms of galaxy formation. We now see galaxies out to redshift 15. Spectroscopically confirmed even almost up to those redshifts. And this is really a change in how we can probe the universe. And of course, this is tremendously exciting, but these galaxies are very bright and they've formed really the tip of the iceberg in terms of what we can see in the universe. These are really, really bright galaxies. And what we think is happening is that most of the star formation, most of the radiation that also does the reionization later on, which we'll come back to, is actually done by lower mass galaxies. So this, even though it's tremendously exciting and we learn a lot, it doesn't tell the full picture. Of course, also, it's not just JWST. Once you have those objects, you follow them up, right? Also, ALMA is now detecting these objects at these very high redshifts. So you can really do diagnostics of those very high redshift galaxies. Again, it's super exciting. So what can 21 centimeter cosmology still tell us, right? We might say, okay, let's all go home, right? We're probing that regime now. Of course, in the end, what we want with 21 centimeter cosmology is to connect that fast sea of neutral hydrogen at very high redshifts, right, from which these stars and galaxies form to those actually, to the actual galaxies themselves, right, which really, as I said, form the tip of the iceberg. Right, that's the name of the game, right? They're really complementary probes. The 21 centimeter signal of hydrogen probes more or less the entire volume of the universe at these high redshifts, from relatively small to very large scales. Now, it's extremely difficult, right? This is certainly not an instant satisfaction game if you're into it, right? I've been into this for more than 20 years, right? So this is not an easy thing to do, but I think when we make this detection, right, this will be extremely exciting. And as I will show today, at least from our side as well, but I think this holds true for HERA and MWA as well, the community is really making progress and understanding the systematics in these observations. So we're setting deeper and deeper limits, and we're now probing into astrophysically interesting regimes with the 21 centimeter signal, even though we haven't made the detection yet. Right, so this is just a nice movie, and for most of you, right, this is bread and butter, and some of you might even be involved in this. But of course, there are also several people in the audience that are not from the 21 centimeter cosmology background. So this is just a simulation from higher redshifts to lower as the universe reionizes. So this is really a reionization simulation mostly, right, where you see the galaxies form, and then these galaxies, their radiation is slowly ionizing the intergalactic medium until it's almost or entirely ionized, roughly we think now between redshift 5 and 6. So with the early first generation of these low frequency telescopes, we were really trying to probe this epoch of reionization, but with instruments like NanoFAR and SKA, upcoming SKA will try to probe higher redshifts as well, those of the cosmic dawn. Now, what do you really probe? You're probing basically the brightness temperature of the 21 centimeter line. And I always like to show this equation. It's the only equation in the talk, right? That shows how this brightness temperature is actually a function of baryonic density, the ionization, cosmology, but also the spin temperature. compared to the radiation, in this case, the CMB temperature, and peculiar velocity. So there's a lot of components going into that brightness temperature field that you hopefully measure as function of its spatial domain, but also as function of time, because you're looking as function of redshift. And then ultimately what we hope to do is invert this by measuring this, learn something about the cosmology, about the density field, the ionization, spin temperatures, and ultimately also peculiar velocities. So our goal is simply to invert this equation. And different regimes have different emphases in this equation. For example, reionization, of course, this X here, the ionization component, is very important. Spin temperature is less important. The cosmic dawn, the spin temperature, is one of the most dominant components in this equation. Right, and then if you do a simulation like this and make a slice through time or redshift or frequency or look back time, what you will see is, of course, the density fluctuations, high redshift, also the brightest temperature fluctuations, which are relatively small at high redshifts. But you also see that the signal goes from emission to absorption through different phases, from the dark ages to the cosmic dawn to the reionization epoch, and then at some point you see the H1 disappear. Right, and again, I like to show always this as well. Right, ultimately, what we, at least in the first instance, try to measure are the power spectra and the global signal of 21 centimeter signal done with different types of instruments. And as you can see, as you change the parameters of the model, the signal significantly changes. So that really means it's a diagnostic of what's happening in the intergalactic medium and with these galaxies. And again, there will be talks this week that say much more about this. So let me now move immediately to what we are doing. So what I will show mostly is about LOFAR and NanoFAR and recent progress. So I'll skip over quickly what we've done in the past years and actually the progress we've made last year and are making this year. This is all part of the CODEX program, which is funded by the European Research Council in an IRC advanced program. It actually contains more than just LOFAR and NanoFAR, but this is what I will focus on. And the PIs of the program are here, and Flora is here as well this week. Of course, this is not something I or Flora or a few of us do together. This is really large teams, right? This is some of the meetings we had recently of the various teams. This is just a general 21 centimeter cosmology meeting where many of us came together as well a few years ago. With this program, we try to cover both the epoch of reionization and the cosmic dawn, mostly with LOFAR in HBA mode and with NanoFAR, which is effectively, let's say, a LOFAR LBA on steroids. I always say it's a much more powerful instrument than the LOFAR LBA, just because it has much more collecting area. So it's much, much more sensitive for the 21 centimeter signal during the cosmic dawn. This is all the things under this CODEX program, but again, I will focus on these two. Now, where do we look with these telescopes, right? So this is more or less a snapshot of the northern sky as seen from the LOFAR telescope, right? You see the Milky Way, the spur here. You see the North Celestial Pole, and the North Celestial Pole is one of our focus fields. It has some good properties. It also has actually some bad properties. The good properties are that it's visible all year round. And if you point at it, the sky rotates there. So LOFAR, which is a phase tracking instrument, does not change its beam as you point there. So those are good properties. Some bad properties are that it's actually not the best field in terms of radio frequency interference. It's also not the best field in terms of leakage from the side lobes of bright sources, as we have figured out more recently. But we also look at the field 3C196, which I will show some new results on. And with NanoFAR, we're also looking at NCP, and we're now looking at other fields as well. So what is our status with LOFAR on these observations? So by now, we've collected about 3,500 hours of observations with LOFAR HBA on the NCP and 3C196. So if we detect a signal, it's there in this 3,500 hours. We're not collecting more data. We are collecting it with LOFAR HBA, as I mentioned. These are these sort of black boxes here. There are 24 tiles of 16 dipoles each. They extend very far out here, even into Europe, but most of the sensitivity we get from those inner baselines. So this is the instrument that we use in terms of LOFAR. So the high frequency HBA system of LOFAR. So just to come back to that picture I just showed, that was this one here. If we just do a little bit of a different projection here, you will, now the NCP is shown here. So it's a relatively dark spot on the sky, maybe not the darkest spot, but relatively dark. That was also why it was partly chosen. If you zoom in with HBA tile observations with LOFAR, and I will not talk about this, but this is a wide field of view of that NCP field here, roughly this box. And you zoom even further in, this little black box here, this is really what we are observing with beam-formed LOFAR LBA. This is the field of view, ultimately, of this entire sky. Not this box, but the box within this box is what we observe, about 4 by 4 degrees. So that is where we get our sensitivity. Now, the approach that we take is, right, we have this, this here, but what you see here is obviously not like 21 centimeter signal. These are all the galactic and extragalactic foregrounds, right? You see diffuse emission here. This is galactic diffuse emission. It's also partly polarized. And you see very bright point sources, which are mostly extragalactic sources and some galactic sources, like Cas-A. So our approach is that we want to remove most of those foregrounds. So the approach we take in LOFAR is not the one taken, for example, by Hera and some of the other experiments where you do foreground avoidance. So all the yellow and red bits are avoided in those experiments. What we try to do is subtract these foregrounds and get rid of most of this so that we can extend. And this is, again, for some of you, very technical, but this is sort of a relatively clean window in terms of observation in terms of a two-dimensional power spectrum. This is spatial and along sort of along the line of sight in terms of a power spectrum. Again, it's very technical for some that are not in the field, but this here, if you don't remove the foreground, it's inaccessible. So our approach is to remove those, and we can do that because most of the foregrounds are galactic, are spectrally smooth, but it's not easy. And I think we'll hear more about this maybe in the next talk by Florent, how we also remove this via Gaussian process regression and other methods. So now I fast forward very quickly on what we have already presented in terms of power spectrum upper limits in the last few years. In 2017, we came out with the first paper where we looked at 3 redshifts on about 1 night of data, about 8 hours of data in total. So that was the first, and that was by then the deepest upper limit. In 2020, actually, we went for a deep analysis of a single redshift. That is shown here. And if you look at it carefully, so this is the upper limit in terms of delta squared. So this is a millikelvin. So right, again, the spatial K mode and along the line of sight K mode. Oh, sorry, not this is the power spectrum, of course. This is the strength here, right? This was the upper limit. But if all went well, we should have reached this more or less. So this is the noise power spectrum, so we don't even reach the noise. So that means there's something in that data that is what we call excess variance. And we're trying to understand, and we'll show results on that in a moment, that we're making good progress on understanding what this is. So this was already a very good and deep upper limit, also then the deepest upper limit at this redshift, but certainly not as deep as we in principle can go. And if you look at, again, at this two-dimensional power spectra in terms of the ratio between what we still see and what we think the thermal noise is, you see that there is some additional component of an order of magnitude, depending where you are in the power spectrum. That's not good. It means we can't go as deep as we hope to go. So this excess variance we also know is largely incoherent. That's in some sense good because it averages down, but right, whatever you do, you will not beat this because it doesn't average down faster than the thermal noise. So in principle, we need to mitigate this, solve what problem this is. Despite that, we put out already in 2020 several papers on the astrophysical interpretation, because these upper limits were sort of starting to probe the upper envelope of what we called exotic models. And that was true. So you have a range of models, of course, with a signal. We're sort of starting to probe it, but these are very extreme models. But this was published in 2020. But we're now in 2024, 25, so what have we done in the meantime? So the first thing, or not the first thing, but the thing we did recently is reanalyze the data from 2020, but in a different way, because we've made a huge progress on this Gaussian process regression. And all the upper limits that we published include this excess variance component. But if we understand either statistically or what this excess variance component is, and we can model it, we can do a bias correction. Just like in the power spectrum, we do a noise bias correction, we can do an excess variance correction as well. So that's what we try to do in this paper here. And if you do that, your upper limits go down quite significantly because you take out that big component. The question is, of course, how reliable is that bias correction? We understand the thermal noise very well. We understand the excess variance less well, but our total model is consistent with thermal noise. So we can bring the limits down quite significantly. So we could bring it in principle down, but we're conservative. We're not using these limits from what we published previously, which was more or less in this red box here, to these numbers. In the future, we hope to use these numbers rather than these numbers. So this is one progress we made in understanding and modeling the excess variance. So if we can do that, the upper limit here will go from 107 to 29 millikelvin squared. And that is really probing close to the astrophysically interesting models. We made a huge progress on RFI excision modeling of the beams, understanding the ionosphere, sky models, direction-dependent calibration. I will not talk about anything, but in the last few years, we've spent a lot of time improving our algorithms. We have obtained much more compute power now. We have 2 GPU clusters now, codecs here. This one is 4 or 5 times faster than the older machine. So in the coming year, we'll be using this to process our data. We made enormous progress, and this is largely thanks to Florent here, in the way we process the data. Again, everything in red has been improved since 2020. So this is, if you zoom in on this, you'll see this field here, right? And if you subtract off our sky model, not everything is gone, but these are largely faint sources that later on we remove with Gaussian process regression. But our biggest enemies are actually CAS and Cygnus A. If you make a big zoom out, almost everything you see is the North Celestial Pole plus CAS and Cygnus. Even after we remove them, that's not perfect. And this is really leaking through in our power spectrum. So in the future, we really need to work on removing these sources better, and we think this is due to direction-dependent calibration errors. Again, this is our current result. This is now has been submitted and hopefully soon accepted paper. Right, so previously you saw we were roughly at a factor of 13. We've now gone down to a factor of 6 above the thermal noise. So that's a huge, it's exactly the same data. So with all these improvements, we're doing much, much better on the same data. But there's still this excess variance. This excess variance actually correlates as function of how close you are observing an LST and where you are in the power spectrum. And it's clear that it's correlated with the foregrounds. So we think this is a problem that has to do with the beam moving on the sky and the beam not being perfect. So we're not subtracting the data perfectly from, we're not subtracting the foregrounds perfectly from our data. Okay, but overall we have made a huge improvement. So everything purple means it's much better than we had previously. So is this the ionosphere? This was one of our worries. So we went through this in a recent paper, and actually the conclusion is no. If you look at the extra residuals of the ionosphere, if you go through the full end-to-end pipeline that we use using ionospheric simulations, the ionosphere is not the culprit. So we can put that aside. Excess variances, there's maybe a little bit of extra noise, goes down very quickly, but it's not even close to the level that we see. So we can write the ionosphere off as the culprit. What we do think is happening is that if you take a beam model, as you think it is, and actually look at the true beam model, because there's some tiles and dipoles broken, it's actually quite different. And we think that the difference in what we use as a beam model and what the beam model really is causing this. And we're doing those simulations at the moment. We believe also based on these coherence results that I just showed, that it's the beam and errors in the beam that are our biggest enemy, apart from radio frequency interference. So where we stand now with LOFAR, so this was the 2020 result. Now based on the new analysis, this is the new limit. If we did the bias correction, we should be even much further down as well. But we also extended it to 2 different redshifts, so we also have these new limits. And this is now, as I said, submitted and hopefully soon accepted. Okay, we're also doing, but maybe there will be a talk later on, so let me quickly go over it. We also submitted an astrophysics analysis on this as well, because we are now probing much deeper into the astrophysical models. Let me quickly actually skip over this, because I only have, well, 5 minutes roughly. All I have until I start a little bit early. I'm taking use of this extra 2 minutes. So I'm going to 25 if you want. So we have now a second field because we have this axis variance. So we started to look at this second field, which for a while we neglected. And this is the 3C196 field. And 3C196 is a very bright source in the middle. That is 3C196. It's 80 Jansky. We thought it would be good as a calibrator. And it actually turns out that this field is really, really good. And not because there's 3C196 in the middle of the field, but it's because the field has seemingly less leakage via the side lobes, and it's also less prone to ground plane RFI source, because it sort of averages away when you create your images and your power spectrum. This is the field. This is with everything in it. This is when we remove the sky model. So you can see we empty it out pretty nicely. Right? All of these side lobes, all of this stuff is now gone from this very bright source and everything else in the field. And then after this, we analysis with Gaussian process regression, we remove everything that's still left in here. Also, when you look at it in 2D, now I didn't show this from the NCP, but it looks much worse than this. It looks pretty clean. You would see side lobe leakage from CAS A and Taurus A here, but maybe you see something here. I can tell you that for the NCP, this is much worse, and we need to cut out this bit in order to remove that leakage. Also, the model we built is pretty good. It's sort of consistent with the data and the model are consistent with ratio 1, of course, with some noise on it, so that's also good. But what is very nice is that most of the power spectrum, at least up here, is more or less consistent with thermal noise, and that's really what we want. But you still see this axis variance, but it behaves a bit differently than in the NCP. Still not as it's not as high as for the NCP, but there's still something here. So it's not gone. This is just a comparison. And this is the current upper limit as will be submitted very soon in a paper by Emilio Cacotti. So this is now the upper limit here. But again, right, there's excess variance, but it's not as bad as the NCP. And if you actually compare them, then this is where we currently are with the 3C196 field compared to a similar amount of data or even more data for the NCP. So we can see it does much better than the NCP. We expect if we would take the same 140 hours as for the NCP that I showed just now, that we will be down here. So that this field seems to be behaving much better than the NCP. Let me now quickly in the last 3-4 minutes go to nanofar. So this is really right what I showed are the limits on the epoch of reionization, redshifts. What about the cosmic dawn? Now for that, LOFAR is not sensitive enough. We need to go to nanofar, which has about 4 or 5, 6 times the collecting area of the LOFAR LBA. So this is what it looks like at night, although this might not be a night picture, but just a darkened day picture. I'm not sure, Florent. I think it's a bit of a cheat. But it's a nice picture, right? So this is what the dipoles look like, but there are about 1,800 of those spread over many mini arrays, and it has an extremely dense core, so that gives it a lot of sensitivity in terms of surface brightness, temperature on the scales that we're probing. We built a very sophisticated data processing pipeline that combines, of course, things that we already did for LOFAR. It has been fine-tuned for this. So we have now an automated pipeline that can process hundreds and thousands of hours nearly automatically. Again, this is the fields with the sources in them, and then if you subtract, again, right, we sort of hit the confusion noise, and after that, you can't subtract much more except via Gaussian process regression, which again, Laurent will explain in more detail. These are just various components which I will not go into, but again, the first results that we had are have an excess variance. So this has just been published last year. It has a huge excess variance. So again, this is on the NCP. This is not maybe necessarily the best field. But another problem with nanofar is near field RFI, at least in the first stages. There were a couple of RFI sources. So we recently developed techniques to identify these RFI sources. This, for example, the electronics cabinets. This one is still an unknown RFI source, but not as bright. This one is now being mitigated by just improving the Faraday cage around the air conditioning of the electronics cabinet. So this is work that has been done and published by Satyapal Munshi, and it's just been accepted last week, this paper. So we built, or he built, effectively a 3D model. You can model these RFI sources, so you identify these two sources. You can make models of their spectra. So one of the next steps is now to subtract these RFI sources from the data to improve the power spectrum limits and reduce this excess variance. But another problem that I mentioned is that you have side lobe leakage of bright sources in the far side lobes, right? Cas A, Cygnus A, Taurus, etc. So we looked at other fields as well. We found a few that are interesting, but the most interesting is NT04 field, which seems to show the least side lobe leakage. So these are the power spectra. This is the NCP, but this field, NT04, is by far the best field. So we actually are collecting a lot of data on these fields. This is with the sources in. This is with the sources out. I'm almost done, Ilian. Don't tackle me yet. This is, again, this is being written up now by Satyapal, but we are reaching now much deeper upper limits. So this is, again, what we published on the NCP just a year ago. This is where we are already on this new field. A little bit more data, but that's certainly not making up this difference. And we're starting to reach astrophysically interesting sources after 26 hours already, models after 26 hours. So this is where we are compared to previous results. These are now the deepest upper limits. And this is overall where we are now as a codex and as a LOFAR and nanofar compared to the other and earlier results as well. We have the deepest results here. We are quite deep here. Here is a little bit deeper at this somewhat lower redshifts. So what's next, and then I'm done, is that we have automated all of our pipelines. So the next year we'll be processing thousands of hours of data on all of these fields, right? Extending the fields to 3C196. We're doing much more on RFI and direction-dependent calibration, improving these beams, DPR techniques to remove foregrounds. And we do this both for LOFAR and for nanofar as well. So I think when I come back here, hopefully next year or the years after, we'll be showing even deeper results and deeper limits. So we've improved our analysis, algorithmic pipelines, compute resources. We have much deeper limits now, both from LOFAR and nanofar. So I think this looks promising. Every year we make progress, like all the other teams as well, to get to a final detection of the 21 centimeter signal. And we are now starting to process thousands of hours of this data. We already started this, and hopefully we'll finish this processing this year and present next year even deeper limits. Thank you very much.
Questions?
Yeah. Okay, I go. Yeah, so you said that so far, fantastic results from the second field, the CC196. You said that it's only 140 hours of NCP so far, and you have taken 3,000 hours.
Well, yeah, that's a total. I think we have, yeah, 2,500 hours on the NCP, and the rest is more or less on the 3C196 field. Yeah, so we have about 20 times, 15 to 20 times more data on the NCP.
So now with the GPR now being tuned properly, I think, how long will it take to, like, is it the computing?
Well, in principle, I mean, if the axis variance, and that seems largely incoherent in most of the fields, we could just simply go on as we are, but then we will have that axis variance always. So in principle, if we have 15 to 20 times more data and the axis variance is incoherent, we'll just go down by a factor of 15 to 20 in the power spectrum limits. That's still quite far away from where we could be in the thermal noise. But because we think we know what the problems are with these direction-dependent gain errors, right? Basically, our beam is not what we think it is. I think our effort in the next years should be on improving this direction-dependent calibration. Because if you then apply that to your sky model and subtract it, your axis variance will also go down, because the axis variance is effectively a result of direction-dependent gain errors, and maybe RFI as well. But for LOFA, we think the RFI issue is less important. So it's a two-pronged thing. We can go down as we are now by a factor of probably 15 to 20, based on the data we still have. But we think we probably can gain another order of magnitude by improving our direction-dependent calibration. And that holds for both nanofar and LOFAR.
Thanks.
One more, only quick question.
Yeah, quick one, Leo. So you talked about the beam variation. So there are three types I can think of. One is that the beam rotates in the sky. The other is the chromaticity. And other is that the beam is different at different stations.
Yes.
Which one do you think hurts the most?
So all of them. So that's what we're trying to find. We know they vary between stations. In principle, we use different beams for each station if we know that tiles are broken. But we know that right, we don't have a perfect knowledge of this. The gains can also vary as well. So so in principle, we model all of the stations independently for all directions. But that model is too simplistic and goes wrong, especially near nulls. So when you have a very strong null and your source moves through it, your model might say the null is a little bit here, but in reality it's a bit there. That causes huge problems. I flashed over it very quickly. We are analyzing this. So what we really need to do is improve our models around the nulls on bright sources in the far field. I think we can mitigate a lot of this axis variance that way. And that just means that we need to build a slightly different type of direction-dependent gain calibration model than we currently have, which assumes spectral smoothness of the gains. But near null, by definition, you're not spectrally smooth, and also not in time and not in space either. So it sort of conflicts with our model around the nulls. So that's what we need to solve.
Let's thank Ilian again. And